So let's take that next step then from graphing linear inequalities to actually using them to solve problems. And the process that we apply to do that is called linear programming. So we're going to look at two variable situations here where we can solve them graphically for now. The fundamental concepts, linear programming with two unknowns. We have an objective function which defines what it is we're trying to optimize, whether we're trying to find the maximum value or the minimum value. And then we have constraints, which basically restrict our possible values of the variables in that objective function. So for example here, we might have this set of conditions. We have the feasible region is defined by these equations down here, and then this is our objective function. That's what, in this case, we want to maximize that, subject to these constraints. They can be called constraints, but they define what is called a feasible region. In other words, the region in which we can draw answers from. So the fundamental theorem of linear programming, first of all, if a linear program problem is bounded, in other words, the feasible region has constraints on all sides, and that's what we're going to start out with, then the solution is going to occur at least one of the corner points of that feasible region. So let's use this to solve a linear programming problem, and then we'll discuss why it is true that it has to be at least one of the corners. So we're going to give you this problem here. This is our objective function. We want to maximize the value of p there. So we want to pick the values of x and y that give us the largest possible value of p, subject to those constraints or these limitations on x and y. So the first thing we're going to do is we're going to graph those constraints. X plus 2y is less than 12. That gives us this line across here. 2x plus y is less than or equal to 12. That gives us this line here. And then, of course, x is greater than 0. That would be this line. Y is greater than 0 is this line. This is why in the last section we blacked out the part that wasn't the solution, because we black out everything, and the part that's left not blacked out is our useful region here. That's our feasible region for this problem. So the solution, the values of x and y that we can use, lie in that region. Now we've got to figure out which one of those points maximizes that function. So we've defined the feasible region. Now the question is, which one of those points in that feasible region gives us the maximum value of that objective function? And as we said, one of the fundamental principles of linear programming is it occurs at the corners. So we have to locate those corners. The x is greater than 0 and y is greater than 0 intersect at the origin, so that's 0, 0. Other intersection points are 6, 0, 0, 6. That's just where the other lines hit the axes. And then we have where these two lines intersect each other, which ends up being at 4, 4. Now this is going to require you to go back and review some of your linear algebra, introductory algebra, solving a system of equations to get that point. So now then, we put those points into that objective function, p equals x plus y, to get a value of p. Put 0 in for x and 0 in for y, well, p is 0. 0 plus 0 is 0. 6 for x and 0 for y, we get 6. 0 for x and 6 for y, we get 6. 4 for x and 4 for y, we get 4. So the maximum value of that objective function comes at the point 4, 4. So that's our maximal or optimal values of x and y to maximize that function. So now why is it that the maximum or the optimal value has to occur at one of those vertices? Well, we're using linear equations, remember, so our objective function is going to be a linear equation. In this case, it's p equals x plus y. So whatever the value of p is, it's going to be a line with a slope of -1. So if we try different values of p equals 10, well, that line doesn't even go through the feasible region. In fact, anything larger than p equals 8, it's going to totally miss the feasible region. And of course, p equals 0, it's going to go through the origin. So any value between 0 and 8, that line is going to go through the feasible region. Well, you'll notice that maximal value, it's either going to clip one of the corners here. If we change the slope, if we made it a steeper slope, it might clip this corner over here, the B. If we made it a shallower slope, it might clip the C. But it's going to clip one of the corners of that because it's a line. The only way it would not be exactly the corners if it actually happened to have the same slope as one of the sides of the region. In that case, that whole edge would be maximal values, optimal values. But notice both of those points lie on that edge. So actually both of those points would give us maximum or minimum values. In this case, we're looking for maximum for that objective function, which if you get 2 points that optimize the objective function, then it's those 2 points and all points on the line between them that are your optimal values. And this is just going to go through justifying again why it has to be one of those corners. They're using a fancy name for those lines I put on there, calling them ISO profit lines or constant profit lines. That's just putting in values of P. I'm giving P a constant value and graphing them and seeing how they intersect. As I explained, it has to either cut off one of the corners or it has to lie on one of the sides of that feasible region. Here you can see changing the slope, it might catch a different corner. So hopefully that is enough of an argument to convince you that the optimal solution will lie on one of those corners. So the method we just used, we graph the feasible region to check to see if it's bounded. Then we find the coordinates of the corners of that feasible region. We put each of those corners into the objective function to get a value to evaluate it. And then we pick the one that gives us the optimal solution, whether we're looking for maximum or minimum value. Note, if that feasible region is unbounded, this method will not work. There's going to be a different method that we use, and even that method will only work if there are optimal solutions. Sometimes we will find that there are not optimal solutions in an unbounded situation. So, bounded feasible region. Let's look at an application. Acme baby food has 2 different types of apple juice. There's a beginner's formula that's 30 fluid ounces with 2 ounces of juice, and an advanced formula, 20 fluid ounces with 12 ounces of juice. Every day, Acme only has available 30,000 fluid ounces of water and 3,600 fluid ounces of concentrate. Profit is 20 cents on the beginners and 30 cents on the advanced juice. How many quarts of each should the Acme make each day, assuming they have unlimited production capacity in each different types? How much should they make each day in order to get the largest profit? So then we'll change it and come back when we're done and change it. How would this change if the profits were different? If it was 40 cents for each container of beginner's juice and only 20 for advanced. So we're going to start out, we're going to let X be the amount of the quarts of beginner's juice and Y be the quarts of advanced juice. Those are our decision variables that we're trying to make a decision on. So we're going to make a little table here. The water available, 30,000 gallons of water, or fluid ounces of water, I should say. It takes 30 fluid ounces of water to create the beginner's juice and 20 for each quart of advanced juice. We have 3,600 fluid ounces of concentrate. It takes 2 for every quart of beginner's juice and 12 for every quart of advanced. Profit is 20 cents for the beginners and 30 cents per quart for the advanced. So those are going to define all of our functions. So this top one here, if X be the quarts of advanced or beginners and Y the quarts of advanced, 30X plus 20Y equals 30,000. That's what we get right here. For the concentrate, 2X plus 12Y equals 3,600. That's another constraint. So those are our constraints. We also can throw in there, can't make less than 0 of the beginners, and we can't make less than 0 of the advanced. We always, a lot of times we have those common sense constraints in there on X and Y. Now they are simplifying these equations. They divide this one by 10 to get that simplified inequality. divide that one by 2 to get that simplified inequality. It really doesn't matter. It's going to graph the same lines anyway, but it's nice to simplify and make them easier to work. As I said, we got to add the x is greater than or equal to 0 and the y is greater than or equal to 0 because you can't make a negative amount of juice. Our objective function then is we get 20 cents per quart profit on the beginners, 30 cents per quart profit on the x. That does not get graphed, that just gets set aside, and that's the function we want to maximize once we get our feasible region. Those are our constraints. So we graph the equations, get our feasible region. So we got 0, 0, 0, 300. There's 1,000, 0. And that point, I'm not sure where that intersects. They'll show us here. It intersects at 900 and 150. So we try those points in that objective function, 20 times x plus 30 times y. And we get the maximum value. The largest value is at 900 quarts of beginner's juice and 150 quarts of advanced juice, giving us 22,500 cents or $225 per day. So we're seeking to maximize, that's why we take the largest value. So because the maximum occurred at point D, we can conclude that the only optimal solution is point D. Remember I said if two of the corners give the same value, the same optimal solution, then any point along the side that connects those 2 points was going to give you that same value, and any of those points could be considered an optimal solution. Here it's only a single point, so that is the only optimal solution. So we're saying the company should make 900 quarts of beginner's juice and 150 quarts of advanced juice in order to get the largest profit of that $225. So what if the profit per quart changed? Well, all that changes the objective function. So we're going to go back to our table here using this as our objective function. Now instead of 20x plus 30y, it's 40x plus 20y. And we see now the largest number comes here, which is producing 1,000 quarts of beginner's juice and 0 quarts of the advanced. So that would be the optimal solution in that case. They would get $400 profit. Now there might be reasons why they would still produce advanced formula even though they would maximize their profit to only produce the beginner's formula. Maybe it's just a social reason of parents want to keep their baby on the same brand of formula. So if the advanced formula isn't available, they're not going to use the beginner's formula because they don't want to switch brands when they get to that point. So this is strictly the mathematical optimal solution, not necessarily the economic optimal solution. So what happens when that feasible region is not bounded? So the trick here, we add a step is once we've set our constraints, graphed our constraints like this, and we get that feasible region, we see that it's unbounded. There are no constraints on these sides here. It goes out forever in those directions. We artificially impose constraints by drawing a rectangle that goes outside of any of the current corners of that feasible region. So A, B, and C are the corners created by our constraints. We make sure that we go well outside that. How far outside really doesn't matter. What we're going to do is we're going to test these points, then we're going to test these points that we created in the bounds that we added, and see if it's one of the points we created, then there is no optimal value. If it's one of those other points, then we're good to go. So we shade the area that's outside of our feasible region here. So we've artificially imposed, remember, this rectangle we put in, so the points D, E, and F are not part of the constraints of the problem. Those are constraints we put on just to see if one of those ends up being it, then this one cannot be optimized. If any optimal solutions occur at one of the original corner points, A, B, and C in the figure, then the linear program problem has an optimal solution. If it's at one of the other points that are created by our artificial bounds, then there is no optimal solution. So let's do an application of an unbounded feasible region. So you're composing a very avant-garde ballad for violins and bassoons. In your ballad, each violinist plays a total of 2 notes and each bassoon plays only 1 note. That sounds boring. To make your ballad long enough, you decide that it should contain at least 200 instrumental notes. Furthermore, after playing the requisite 2 notes, each violinist will sing 1 soprano note, while each bassoonist will sing 3 soprano notes. To make the ballad sufficiently interesting, you have decided on a minimum of 300 soprano notes. So that's the singing that each musician is going to put in, a minimum of 300. To give your composition a sense of balance, you wish to have no more than 3 times as many bassoonists as violinists. Violinists charge $200 per performance and bassoonists $400 per performance. How many of each should your ballad call for in order to minimize the personnel costs? So we're trying to minimize this here. And typically in an unbounded situation, that's what we're looking for. First, the unknowns are X equals the number of violinists and Y equals the number of bassoonists. We know that this implies the number of notes each, so there's constraints on the instruments and on the number of notes. The instrumental notes, remember the violinist only played 2 notes and the bassoonist played 1, and we wanted a minimum of 200 notes. So 2x plus 1y is greater than or equal to 200. For the soprano notes that they sing, each violinist sang 1 and each soprano sang 3. So 1x plus 3y, we wanted at least 300 of those notes, so it's greater than or equal to 300. Now I realize this is a very contrived situation, but trying to find an unbounded situation that was not extremely complex is hard to find. So the next part here is a little tricky. We're looking at defining the number of bassoonists as being no more than 3 times the number of violinists. So we rearrange that to be that 3x minus y is greater than or equal to 0. Now our objective function here, the cost, 200 times each for each violinist and 400 for each bassoonist. So the total cost will be 200x plus 400y. We want to minimize the total cost, so we want to find the smallest value for that objective function for C, subject to those constraints. So we graph our constraints. Y equals 3x, it's right there. Less than would be on this side, so we blacked out the other side. The x plus 3y for the soprano notes is down here. More than would be up here again, so we black out the other side. That's where we don't want to be. And finally, the instrumental notes is this line. Again, more than would be out here, so we black out the other side. So our feasible region is out here, and it's unbounded. There are no bounds out here. So we can just artificially put bounds out there. You know, they say do a rectangle, but really all we're doing is artificially binding this, making sure we go well outside of the points that are already there. So I could have gone all the way up here, or even just as long as I'm outside of the points that are already part of the bounded region, that feasible region, or the unbounded feasible region. So those are the points that are created by our constraints that are given. And these are the values that the objective function you're putting in for the cost is those values. So far, it looks like cheapest would be to have 60 violinists and 80 bassoonists. That'd be $44,000. But let's make sure that there aren't other possibilities. So if I tried like a point, hit the wrong button, a point up here, well, this would go negative. Can't have a negative number of bassoonists, so we can't have any point here. Over here, I could pick any point on the line. Let's pick this one right here. What would that be? That looks like 2 and 6. So probably 200 and 600. Well, that's obviously going to be more expensive. That's way more musicians. That doesn't fit. And any point out here that's outside the constraints, I might pick this point here. That's outside of both constraints. That would be 2, 3, 4, 5, 6, 7, and 3. So 700 and 300. That's going to be way more as well. So generally these unbounded situations, to be totally frank, work best if we're trying to minimize that objective function. If we're trying to maximize it, typically the unbounded situation does not provide an optimal solution. So there we go. Our minimal cost, optimized cost, is going to be $44,000 using 60 violinists and 80 bassoonists. So that is it for this section. The next part is to move on to 3 variables and how we deal with that. We'll do that in our next section.